Hello, my rubber hearts. Today, we're tackling a crucial topic: polymer molecular weight and molecular weight distribution. These concepts are essential in understanding how different types of rubbers behave and why they perform the way they do. We will start with the basic definition of what a polymer molecule is and how it's structured, then dive into what molecular weight and molecular weight distribution mean. And of course, we will look at how these factors affect the properties of rubber used across various industries. So, whether you're a rubber professional or just curious about the science behind your favorite rubber product, this episode is for you. Let's kick things off with the basics. A polymer molecule is a long chain made up of repeating units called monomers. Imagine it like a pearl necklace where each pearl represents a monomer, and when you link enough of these monomers together, you get a polymer chain. For example, natural rubber is made up of repeating units of isoprene monomers. This long chain structure is what gives polymers their unique properties: flexibility, strength, and elasticity, to name a few. Another fascinating example of a polymer chain is cellulose, a natural polymer found in plant cell walls made of repeating glucose units. It provides structure and rigidity to plants, much like a skeleton. Proteins are also polymer chains, composed of amino acid sequences that fold onto complex structures, performing countless functions in living organisms. Similarly, polyethylene is a synthetic polymer used in plastic bags and bottles made from repeating ethylene units. Just like DNA holds genetic information, these polymers have unique repeating structures that give them their specific properties, whether it's the toughness of tree trunks or the flexibility of plastic packaging. Now that we know what a polymer molecule is, let's talk about molecular weight. Simply put, molecular weight is the total mass of a polymer molecule, determined by the number of monomers, or repeating units, in the chain. The more monomers you have, the heavier the polymer molecule, and thus the higher its molecular weight. Polymers are often made up of many chains of different lengths, so they don't all have the same molecular weight. Some chains are long, while others are shorter. And this brings us to the next important concept: molecular weight distribution. Molecular weight distribution refers to the range of different molecular weights within a batch of polymer. Think of it as a classroom of students. Some students are tall, others are short, and most fall somewhere in between. In the same way, a batch of polymer will have some very long chains and some very short ones, and a lot of chains that are somewhere in the middle. In polymer science, molecular weight distribution is described by terms like number average molecular weight, or MN. This is the average weight of all the polymer molecules in a sample, treating all chains equally regardless of their length. Weight average molecular weight, or MW. This gives more weight to the longer chains in the sample, meaning it skews towards the higher molecular weights. The ratio between the MW to MN is called the polydispersity index, or PDI. A PDI of 1 means that all the polymer chains are exactly the same length, but in reality, most rubbers have a PDI greater than 1, meaning they contain chains of varying lengths. Now, let's talk about how molecular weight impacts the properties of rubber. The molecular weight of a polymer plays a significant role in determining its mechanical and physical properties. Elasticity and strength, for example. Higher molecular weight typically means longer polymer chains, and longer chains are better at creating a network when the rubber is vulcanized, the process where we add crosslinks between the chains. This network gives rubber its elasticity and strength. For example, natural rubber with high molecular weight tends to be stronger and more elastic. This is why it's used in products like tires, where both flexibility and durability are essential. Butyl rubber, or IIR, used in products like inner tubes, benefits from longer chains for airtightness and flexibility, but lower molecular weight can make it easier to process. Processability. Lower molecular weight polymers are generally easier to process because they flow more easily during manufacturing. For example, styrene butadiene rubber. SBR with a lower molecular weight can be easier to extrude or mold into shapes, but it may sacrifice some elasticity and strength compared to high molecular weight SBR. Ethylene propylene diene monomer, lower molecular weight EPDM, is often used when high processability is needed, such as in complex extrusion processes for weather stripping. Next up, let's look at molecular weight distribution and how it influences the final properties of rubber. 1. Narrow molecular weight distribution. A narrow distribution means that most of the polymer chains in a sample are of similar length. This can lead to more uniform mechanical properties, but it may reduce the polymer's ability to be processed easily. Silicon rubber often has a narrow molecular weight distribution, which gives it a consistent elasticity and mechanical properties, making it ideal for medical applications and seals. 2. Broad molecular weight distribution. A broad distribution means there is a wider range of polymer chain lengths in the material. This can enhance both processing and performance because the shorter chains make the polymer easier to work with, while the longer chains contribute to the final strength of the rubber. In tire manufacturing, SBR with a broad molecular weight distribution can offer a good balance between processability and durability. The shorter chains help during manufacturing, while the longer chains ensure the tires remain strong and elastic during use. Now let's take a closer look at how molecular weight and its distribution affect some of the most common types of rubber in the industry. Natural rubber. High molecular weight NR provides excellent elasticity and tensile strength, making it perfect for applications like tires, conveyor belts, and shock absorbers. Low molecular weight NR is easier to process but lacks the same level of strength. It's often used in adhesives and sealants where flexibility is important but high strength is not necessary. In the case of styrene butadiene rubber, high molecular weight SBR is used in high performance tires for its good wear resistance and strength. The long chains help distribute stress and improve durability. On the other hand, low molecular weight SBR is preferred for easy processing, like in the manufacturing of shoes or soft rubber goods, where fine detail in shaping is needed. Nitrile rubber. High molecular weight is used in oil resistant applications like hoses and gaskets because it offers superior mechanical properties and chemical resistance. On the other hand, broad molecular weight distribution NBR provides a good balance between processability and resistance to oils and fuels, making it widely used in the automotive industry. In rubber compounding, balancing molecular weight and molecular weight distribution is key to achieving the desired properties. A narrow distribution may be needed for consistency, while a broad distribution can improve both the processing and performance of the material. Rubber formulators carefully evaluate these factors based on the end use of the rubber product. For example, high molecular weight rubbers may be chosen for products that require durability and strength, like tires, while lower molecular weight rubbers are selected when easy processing is more important, like in adhesives or sealants. So, to sum it all up, molecular weight is a key factor that determines the strength, elasticity, and durability of rubber. Molecular weight distribution, on the other hand, affects how well rubber can be processed and how uniform its properties are. By carefully balancing these factors, rubber compounders can create materials that meet specific performance requirements in industries ranging from automotive to consumer goods. And that's it for today's episode. If you enjoyed learning about polymer molecular weight and how it impacts rubber, don't forget to give this video a thumbs up and subscribe to the channel for more deep dives into rubber science. Let me know in the comments if you have any topics you'd like me to cover next. Until next time, stay bouncy, my rubber hearts.